welcome everybody. So we will have a video that lasts almost 30 minutes. We have planned 2 breaks during the course of the video, during which you can ask questions, and of course also after the video. Questions can be asked via the chat or by raising your hand. The questions then will be answered during these breaks or after the whole video. Okay, so if you are brave and have switched on your camera and your microphone, we can bring you to stage, and then you can ask your question directly on stage. And we have a team here out of a lot of experienced PCB experts, so more than 100 years of PCB experience here gathered together, and so there should be no question we cannot answer, hopefully. Yeah, I'm really excited and thankful to have this chance to show you our production, and a warm welcome to all of you. I'm personally a part of Würth Electronik since 26 years, and we are proud to be a part of this AltiumLive Summit as well, and we are proud to show our PCB production plant to you. The plant, which was commissioned in 2016, is one of the most modern PCB plants in Europe, and specialized in high-tech solutions such as flex rigid and embedding technology. And the tour will show the key production steps involved in making a PCB. So I think it's a big chance to meet the mission of the AltiumLive: learn, connect, and get inspired. So it should be a great opportunity to learn, at least.
One thing, normal PCB designer does not really recognize how many processes are behind the production of a PCB. So that's, for customers who come us to see the production, they are always surprised about the complexity of the process. And so that's the most interesting thing for me. I can apply all my knowledge about physics and chemistry and material science, so the combination is so interesting. You ask about the most interesting application I ever had, so that's really difficult to answer. That's one of them, definitely. This is a continuous bending application, always moving for 20 years like this, and it's a replacement of a cable harness in a couch, in a lateral couch for treatment, medical treatment, so radiation treatment, and this has to be very precise and very reliable. So that was one of the most interesting applications I ever had. So miniaturization, of course, the components itself, they are even more miniaturized over time, and as well the housing. So if you think about smartphone, if you think about portable electronics, everything has to be miniaturized. So starting with the components, but as well removing cables, connectors, and using flex rigid is quite a perfect way to do that. So reliability is another aspect which is very important. For example, this is from a pistol tool, and pistol tool for professional assembly of motors, for example, and if such a pistol falls to the ground, there is a high impact of shock, and this could lead to an interruption, and with flex rigid that problem has gone, definitely. So high mix from gifts up to high professional medical applications, so racing technology, professional tools, so it's a big variety we are producing. So this is the area for the photo imaging, so that's why the color of the light is yellow, to prevent exposure of the photoresist by the light. I would suppose to start with the material to follow the production chain. So we have to go some more steps. So behind this wall we have the material stock. So it's a tower, you can see it from outside. All the base material is inside here, and that's the place where the production starts. So take the material according to the job. So it's a core material with copper on it, there is a pre-preg material, there is copper foil, there is flex material. So everything comes out fitting to the job. With this material, the job goes a few meters along here. So these are the lines for the inner layer production. That means that's a cleaning process, etching process, and then the panels pass into the yellow room for the imaging. And inside the room, the yellow room, there is the application of the photoresist to the panel, and so that's done here. You can just see the panel coming here. So that's the outer layer, by the way, but it's similar to the inner layer process. So here the panel is copper, just copper on the outside, and after the lamination process you can see the photoresist on the whole surface. So then we have a stack just to match all the different speeds, and this is the exposure machine. So that's a laser exposure. We don't need any artwork in films, as we say. So it's a direct imaging via laser process. So that's the outer layer. What we can see here is a panel, and one issue you immediately can see, there's a lot of area outside which is not used. So that's not perfect. So that's one of my concerns every job, to try to fit it best to the production panel. So you can imagine 1, 2 more PCBs would fit on the panel. So that's everlasting discussion with customers. So this is the outer layer, as I said already, and everywhere we have the blue color. There is the base copper material underneath, and this is etched away. So what we can see in the bright, shiny tin surface, that's the artwork which remains finally. So this is the inner layer line, and after the exposure, which is done inside, the next step is the etching process. And the next process starts here. This is the etching line. So this is cleaning and removing of the not exposed laminate. So the photoresist which is not exposed is washed off, and this is the etching chamber. It's a separate housing which is important for the protection of the whole company and the people working here. So that's a special exhaust system with that. So after the etching process, the panel comes back on this line, which prepares the inner layer copper for the lamination process to improve the adhesion between the copper and the pre-preg material. So You can see the copper is already a little bit darker compared to the shiny, bright copper after the etching process. So there is a special treatment of the surface. So after this, all the different layers are matched together. So we have to walk 10 meters roundabout for the next step. This is a flex rigid department. We see that later. So this is AOI, where we check the quality of the etched structures. So that's what we call the quality gate, just to see whether everything is fine with the etching process, and so that we have the finally artwork which the customer wants to have. So this quality gate. After that, there's the bonding process in the next room, and here we can see a lot of prepreg material which glues the inner layers together. And so that's a pre-bonding step where we have a perfect registration between the inner layers and with all the prepreg sheets in between. After that process, we have a pre-package, let's say, and we only have to add the copper for the outside, and then the lamination process is done. So this is the lamination area. This behind the glass is the layup stations. There are the layup stations where the final application of a prepreg and a copper foil is done, and then the tools are running automatically into this stack, and from this stack it's transported into the lamination presses. You can see behind here we have hot presses where the material, the tools go inside at a high temperature and pressure, and then we have also cold lamination presses to cool it down under controlled conditions. So for the shrinkage of the material, that's very important. So that's the lamination area.
So now it's a chance to ask your questions, if there are any.
So if you wanna ask a question in person, that what we would encourage, you just need to make sure that you enable your video and your audio in the top left corner, and then raise your hand. This button can be found on the top right, and then we can bring you on the stage. I think we have also some questions in the chat that were already answered by you guys, actually, right? Mostly.
Well, the first question with the thermal expansion, basically we try to predict the shrinkage or the expansion. I'm not unmute. Sorry. We try to predict the expansion or the shrinkage of the inner layers before, and after pressing we do an X-ray to measure the actual expansion to adjust the drilling programs.
Thank you, Alex. As you said, this should be an interactive session, so you are able to be brought to the stage if, yeah, here we go. Nick, if you want to enable your video and audio, then we can bring you on the stage and you can ask your question. Here we go. Here's Nick. But here we go. And you can unmute yourself. Here we go.
Now, can you hear me?
Yes, we can hear you.
Hi, I was wondering if this is the only facility that Würth has, and it seems like a lot of the process is not hands-on human, but machine. Is that true?
Well, it's not the only factory. We have 3 factories in Germany, and it's the newest one we have. And yes, we try to have not too many hands-on on the processes.
Okay, great. It's a beautiful facility.
It really is beautiful. When you walk through it, And that also the way Andreas, you explained it, that you kind of compared your facility to a rigid flex design, but everything is kind of like winded into each other to minimize the distance between the stations as well. I can remember you telling that. So we have also Richard, who wants to ask a question. I'll bring you to the stage, Richard. Yeah, I will unmute you. Here we go.
Hey there. Great tour so far. I'm just wondering, the steps that you've shown so far, on average, how long does it take to go from start to finish?
Okay. Who will answer?
I don't find myself.
Okay.
Yeah, well, it depends on the product.
If you have a 4-layer board or a 6-layer board, we are through within 5 days, including pre-production. If you are looking for a rigid flex board, which is having like 3 times, 4 times more process steps, it takes around 10 to 15 days.
And regarding only the imaging processes, how long does this take?
Imaging process? How long? Oh. 4 hours, I think so. Yeah. I think so. The imaging process is 2 hours, and yes.
Well, it depends on the lot size.
Yeah. Okay.
Okay. So there is Matthew. Matthew, I bring you to the stage.
Hello. I had a quick question about what your preferred method is for defining stiffeners for flex panels. So like if you have a completely flexed panel, how do you guys like to have the stiffener defined? Like a small spot or throughout the whole panel, or like what is your preferred?
Okay, I think this is a good question for Klaus Schilmunak, but actually he has problems with his camera, but I think he should be able to change. Okay. So Klaus, you're on stage.
Okay, sorry. Can you repeat the question?
So I think it was about stiffness, if I have understood. Well, how we apply stiffness to a flex board.
What way we do it in the lamination step, and in the final process of the routing, we use a depth milling. So we have an FR4 stiffener and no polyamide stiffener.
So for stiff contacts, especially.
Exactly, for stiff contacts, yes.
Of course, we can also glue stiffener, in, for example, out of FR4 material in certain parts. But our favorite is to change from a lot of stiffness to use flex rigid in a new approach. So I think flex rigid is always a better approach compared to have a lot of different stiffness in different parts and thicknesses maybe. Is that an answer you can deal with?
I was wondering more so if I had a panel and it was all flex and I had like stiffeners throughout it, would you guys prefer to have the stiffener like defined as like a bunch of regions or something that you guys can just route that out and then glue it to the panel? Or would you rather have the individual small little parts, sections where the stiffeners are, and then just manually know where to place those?
Okay, so you mean not a SIF connector, you mean FR4 stiffeners in maybe different thicknesses, yes?
Yeah, sure.
Okay. it depends on the size of these parts, yes, and the number of the parts. With just a few ones, we can do it. We will applicate it partial regions. If there's a lot of stiffening, I would say, area in our production panel, we will using it by depth milling.
So it's always preferable to make a big part of stiffener and then to divide it by a milling process, for example.
Yeah.
Another option is to make it like a flex rigid, to glue the flex completely on a panel.
And after lamination, we perform the X-ray process. That's for the creation of new registration holes. That's an X-ray machine. And after the X-ray, the robot cut is cutting the edges. And after the cutting of the material, the drilling is performed. So depending on the layout, we perform through holes or we perform micro wires laser drilled. And we have different lines. So this is a line where we have the jobs with higher volumes, and this is the line where we have typically jobs with less panels to produce. So that's more flexible here. This line, this is for more volume. And from the other side, you can see then the drilling process. These machines you can buy over the whole world, of course, but the concept of the plant and also the environmental sustainability aspects we regard it at. So we think that's really awesome. And this is a laser process here for microwires. So for tiny laser drilled microwires, this is the area. So laser drilling, of course, is used normally with HDI technology, but more and more we have the same components on flex rigid boards. So we also have a lot of HDI technology combined with flex rigid technology, as the components are the same. So miniaturization in a rigid board as well as on flex rigid board. So after the drilling process, we have to plate the holes, and that's done here in this line. So it's around 70 meters long. First we have to clean the holes to prepare them. Then we have to plate with a thin copper film, and afterwards it's electroplated. That means thicker copper with the electroplating process. So after the plating of the holes, we start a new photo process for the outer layers. So this time it's a left line. So here cleaning, then the photo resist and exposure by direct imaging laser process. So that's the end of the process, and from this point the panels are shipped here to the next process, which is the electroplating process. So that's called pattern plating, as we just plate the pattern here, so the artwork of the customer. So for the material there is a lift, elevator, but we have to walk. So this is the alkaline etching, and normal process flow is like this. So coming from the plating line, from the pattern plating, then going through the line. So first removing the blue material, which is the exposed photoresist, then etching the base copper, and afterwards removing the tin from, which is the etching protector, the tin surface. So that's how the boards look after the etching process. By the way, this is a PCB. You can see the area usage is quite perfect. This is a PCB coming into the Dreamliner for the hybrid light in the cabin. So this is a light behind the white light to give them any colors which is desired. So in the morning you can have a yellow light, in the evening or in the night you can have a blue light. So that's the PCB behind that. So after the etching, so now you can see the final board in a copper way, so a copper surface, and the next process is to apply the solder mask on that. And we still use solder mask, old solder mask, let's say. So we spray that. You can also do curtain coating. We are using spray coating, but we are already at the step to the future using 3D printing. So that could be really interesting for designers to have accurate alignment of the solder mask, for example, and to have the solder mask where you want to have that. So that's a nice option, but we still have to understand the possibilities, the options we can use out of this. But the thing is, additive manufacturing is a thing of the future, definitely. So this is a preparation for the solder mask. So again, a short way from here to here, and then this is an automated line. Nothing in, actually. So this is the line, the coating machine at the start of the line, then curing of the masks, then the imaging again with laser imaging, direct laser imaging, and then the final curing in the oven, which is done outside here. So this is the oven which makes the final curing of the solder mask. And that's all new. By the way, there is a picture at the wall, and this is not a normal solder mask, but this is what we call S-mask. So that's 3D printing, and you can have different thicknesses wherever you want. So it gives you an impression like a picture. So there's no color, that's just solder mask. Which has a color, of course, but green normally.
So we are at our next break. Again, for questions. So if you are having questions, I saw some coming in through the chat, and we will address them as well. Louis sent a question, and you already addressed it. Louis, did you wanna? If you wanna ask the question personally, you can also raise your hand. Otherwise, if you feel more comfortable not to, then we can also first pull Ricardo up again. He has a question. Go ahead.
So in my research, blind and buried vias, which are typically done by lasers, are more expensive, and as well small vias for BGA with via in pad tend to be more expensive. So I guess one, is that true? And I guess the main question is, what will it take for that type of process to become less expensive and more accessible for more customers? Is it a matter of it becoming more popular, and so there's more availability, or is there something else that causes the expense?
So I don't think that it is still true that laser wires are in general more expensive than mechanically drilled holes. If you compare the drilling speed of laser drilling with the mechanical drilling, it's quite different. So if you manage to use a lot of micro wires and don't use plated through holes as in older times, so you may even be less expensive compared to a standard PDH board. So of course, if you have to drill blind wires in a mechanical way, that is normally more complicated and also more expensive. But if you manage to make a clean HDI board, this may even be less expensive. And you can save some layers maybe, so which drops the price again. So I think HDI is very common actually, and it's no longer an expensive technology in general.
Okay, I think I'll have to ask you guys for a quote then, because that's different from some of the other answers. So thank you for that.
All right, thank you, Ricardo. So there are some questions that came in through chat, and if you prefer to ask the question in person, just raise your hand. But I'm just going to read it. Let me know if you already answered that question. But Jeremy Bloom, he is asking, is green the preferred solder mask color because it provides the best contrast for AOI machines? On modern lines, can any solder mask color be used just as easily?
For us, it's like Henry Ford said, you can order everything in green, in any color if it's green. So we use green. It's very common for PCBs, and but I think modern AOIs would also recognize any other color.
Okay, great. So we got Jeremy Waller who wants to be brought to the stage. I'm going to bring him to the stage right now. Hi, Jeremy.
Hello. I was just curious, are you able to recover the copper from the etching process? And part two of that, are you converting any of your lines to an additive copper process to looking forward into the future?
Well, the outer etching, we recovered the copper. There it's very much possible, and we do that. And the through-hole plating line is more or less an additive process, but not a semi-additive process. So we are not printing copper right now. It's not so easy to do so because copper is very corrosive, and you need to apply a lot of heat to bond copper on anything. So there's a lot of development to do to print copper. Does this apply to your question?
Yeah, I think so. I was mostly just curious how much of that copper just is lost in the process. It seems like a wasteful process, to be honest. So I've always wondered about that.
It's a lot of copper, but like I said, and on the outer etching process, we are recovering the copper, and it will then be recycled and be again used for the anodes or for the copper foil.
Nice. Just to add to Jeremy Blum's question about the solder mask colors that he brought up just a minute ago, I've also seen some fabricators call out that other colors like blue or black have less adhesion to copper. And, I'm just curious if that's pretty widespread in industry, so that your solder mask dams might not be as easily held with black or blue compared to, say, red or green. Is that true?
I think the green color had the better properties. the green color is for the nature the better way as a black color as a red color. The red color is nice, yes, but but green is for the long time better. Yeah.
Thanks.
And there is also for the green color, there is a physical thing, because to expose the green color, you need less energy to do so. So it's a very efficient process in exposure.
Interesting. Thank you.
Thank you, Jeremy. All right. Are there any other questions at this point? If there are, just raise your hand. Otherwise, we can keep going.
Benjamin, we could also do another quiz.
Oh, is it time for another quiz? Sure.
Yes, I think so.
Let's do it.
So we have already seen the process of the drilling, and I just start a quiz for that. So the question is, what is the smallest mechanical drilling diameter, so tool diameter? We have three options: 0.3, 0.2, and 0.1 millimeter. Okay, so we have around about 50% of the participants have voted. So, okay. So another 10 seconds, I think. So there's a more or less clear picture. Okay. So I will end the quiz and let's see what is the result. So you have voted mostly for 0.2 millimeter, which is already very thin, of course, but indeed we already are using tools with a diameter of 0.1 millimeter. Of course, you have to regard the aspect ratio, so we cannot drill 3 millimeter thick PCBs with that, but we have tools indeed with 0.1 millimeter for mechanical drilling. So it's quite astonishing. Okay, Benjamin, so it's time, I think, to continue the video.
Then we enter the area of surface finish, where we have the ENIC process, so that's electroless nickel immersion gold process, which is most common for PCBs, especially for flex rigid PCBs. So ENIC is the surface of the choice. So these panels have to be treated, so they are waiting for the process. Takes around about 2 hours, the process. So they are waiting to be processed, and there are different processes in a queue, and it's all fully automated. So after the ENIC surface process, next step is mechanical process, so routing the contour. So I have to go down once there again. Hello, hi again. So this is the mechanical department for the routing. So we are doing the contour routing as well as the depth controlled routing for flex rigid and semi-flex technology. So that's all done here. And as well, we have the laser, special pico laser as it is called, for the cutting of flex material. So here we are doing the cutting of flex. That's a special laser which has not that high energy input into the material, as energy input always leads to carbonization, and you don't want to have carbonization at the contour. So that's a special laser which is perfect for the treatment of flex materials. So here all the yellow chops are special chops or are flex rigid chops normally. So to see it immediately which kind of technology you have. So we have yellow cards here, and there is a depth controlled routing to remove the rigid part of the flex rigid. So here you can see the traces where the routing has been performed. A lot of crazy contours. This one is also nice. Oh. That's another camera PCB. That's a stack up of 12 layers. 4 layers of them performed in flex material. So it's a high performance, sophisticated camera. And finally it's bended like a cube. This is a flex area. So we have to cut 2 times. And finally, if we route the outline contour, this falls out, this rigid part, and then we have the flex area here. As the flex is on the other side. So here you can see the other side. This is a cover lay in the flex area. And here you can see the back side, which is depth controlled routed. So that's a flex rigid with 1 flexible layer outside. On this side it's a flexible layer, and this is a rigid part. So this is already after the final routing process. So this is a final shape and the final board. And again we have the stock behind the machine. You can see the panels which are a little bit more outside. They are already processed. And the boards which are more inside, they have to be processed. All the boards are washed, if possible. Of course you cannot wash small PCBs which fall through the machine, but especially all the delivery panels, the delivery arrays, they can be washed without a problem. There's also an optical inspection which is performed by the machines here. We call them, or they are called Whisper. So we have 2 possibilities of checking. It's based on people or based on machines. So especially for higher volumes, automotive application, for example, we use the machine. It's a higher throughput, and yeah, there is no human error in that, of course. But it's not applicable for prototypes or very small volumes, of course. And finally, the final inspection is done by human. And most of the machines are based on needles. So flying probe testing is very commonly used here. So after the electrical testing, we also have a lab here for making cross sections, making different testings. One test also here. So where we are doing the check of the dimensions for the final inspection report, for example. Here we are testing the dimensions. Here is another possibility of doing checks and measurements. So we have a special testing here, which is called Interconnect stress test. So to perform thermal cycles and to see the reliability and whether there are failures during this temperature changing. Ah, doch da hinten. Ist er da versteckt? Ah ja, okay. Okay, danke. So this is what I called or mentioned already, the IST testing, and you can see the cross-section picture here. That's the bladed hole. You can see the inner layers here. So you should imagine this is the barrel is here, the through hole, the bladed through hole, and this is an inner layer. which is connected to the barrel. You can see the treatment of the copper foil. So this is a rough side, the treatment. So here is a core and here is a pre-preg. And of course we have to check after the test if we have failures, what's the reason for the failure. Is there an issue with the material or with the process, or is it just aging finally? So here you can see, sometimes you can see glass fiber from the base material. So this is from the drilling process and from the preparing for the plating process. So if it's rough, that's normal, and it helps to make a good adhesion to the hole, to the wall. So now, after checking the dimensions and the quality, we do the final inspection. So checking that all the documents are available, that the volume is perfect. Hello. That's done here. And if the boards have passed the final inspection, so they are shipped to the customers. Ja, komm, lächeln. So this is a shipping area. You can see a lot of parcels here, making our customers happy prior to Christmas, hopefully. So this is a shipping area. And then the job is done.
So now we arrived at the end of our tour, and again we would like to take questions. And I think, Andreas, maybe you have a quiz while we wait for people to raise their hand to bring people.
Yes, forward. Indeed. After we have seen the whole planned tour, there is a quiz for that. I will start it now. So what do you think? What does a PCB production with building for a capacity of around about 400 square meters per day should cost? So you have 4 different possibilities. Maybe a little bit surprising to you about the numbers. So there's a big range. And there's a big uncertainty with you, I can see. Okay. So the trend is to the middle, as every time. So now let's wait another 5 seconds, then we will finish this quiz. Nearly everyone has voted, so I end the quiz here. And the result is, most of you think $63 million or $125 million, which is quite a lot. But to be honest, it is $170 million. So it's not that cheap. But of course, it's quite a unique building. It's quite a unique instrumentation and everything of the machine. So you can just roundabout calculate one machine is $500,000. Okay, Benjamin, are there any questions?
If there's somebody that wants to ask a question in person and wants to be brought to the stage again, you can raise your hand. Otherwise, I think we can pick a question. There's some that came through in the chat. Some of them already answered. Let's see. So yeah, I mean, the cost that we just saw needs to also be considered. We need to also consider all the automation that you have built into that facility. And when I was at your facility to visit you, you mentioned that you are one of the most modern facilities in all of Europe. Can you?
Yes.
Can you maybe elaborate a little bit on that?
Yes, I think one of my colleagues is perfect to answer this question. I just tried to unmute Alexander Staud.
I'll do it myself.
Okay, now.
Well, there's a history behind this new factory, and the history is that basically we started here in 74 producing PCBs, but in 2014, during the holidays break on Christmas time, the factory burned down due to a technical problem. So we had the luck to rebuild this factory, and that's why it's so new.
Yeah. Another question from the chat is, what is the smallest PEM nut you can install in PCM? Not sure if that, maybe that was not answered yet.
Well, what is a PEM nut? That's why we didn't.
Davy Baker. Davy Baker, if you're still here, would you like to elaborate on what you mean by your question? Maybe you wanna ask directly. Let's see. What is the smallest PM nut you can install in PCB? Okay. Well, let's move forward. Let's see. Oh, here, Benoit Borduc, if I'm spelling this name correctly. With regards to the first question about 10 layers process, did you include flex rigid, buried vias, micro vias, gold plating, all the processes?
No. If you go with a rigid flex board, you have easily 120 process steps.
Mm-hmm. Okay, and
so it was just a basic technology, as I mentioned, so without any special blind wires or buried wires. Okay, but gold plating is not that complicated, as well as microwires. If the stack up is dedicated for laser drilling through a 1080 pre-brick, for example, so that's just one additional process to make wires, microwires on the outer layer. So that's not that big difference, but of course, flex rigid is another question on different technology.
Mm-hmm. I think the last one that we have here is, oh, Bernd, you already answered. You already answered that last question in the chat. Okay, cool. Maybe we give everybody the last chance to ask a question.
So we already can say good morning here in Germany.
Oh, we have someone with a question. If you would like to make your camera and your microphone available. Perfect. So we have Luis. Hello.
I was curious, based on this question about the hard gold. I saw that there were some PCBs in a panel with hard gold. Is there any requirement regarding the panelization of such designs? Because as far as I understand, the hard gold comes as a extra step, right?
Well, yes, it's an extra step, and what it's electroplating. What you need there is, if you cover basically the complete panel except where you need the hard gold, you need an electrical connection to the frame of the panel to get this hard gold on. So this is one thing, to get this electrical connection outside of the PCB. This would be one requirement for hard gold.
Okay, so the panel construction can be done normal, and then is this extra?
Yes, it can be done normal. In the earlier stage, it was outside and we cut it via a V cut. But now we are doing that on the machine with kind of a deep routing. So no specification on that.
Okay, thanks.
You're welcome.
Thank you, Luis. We have Dan who wants to join. Hello, Dan.
Hi. Thank you so much for the tour. It was very, very impressive. You mentioned about additive being a probable path of the future. Are you considering additive in the old format, like the old photo circuits processes kind of from 30 years ago or so? Or are you considering additive 3D printed additive?
Well, we are looking in both directions. If we look in additive manufacturing, we look to replace standard processes on the one side. On the other side, of course, we are also looking in 3D printing of a whole PCB. But at the moment, it's not very competitive on large volume, but it's kind of an additional process. So the larger you are with the PCB, the more interesting is to be on a normal process. The smaller the PCBs are, the more competitive the 3D printing is.
And just as a follow-up, are you considering for the maybe medium to far future, I guess, printing 3D printing not only of the dielectrics and the conductors, but also of the passive components?
Well, we do print passive components at the moment in a silkscreen process, but it should be easily be done in an inkjet process. But the demand on this printed passive components is not that high.
Not yet, no.
Well, we have it for 10 years and we don't see that it's increasing.
Thank you.
Thank you, Dan. Dan, where are you calling from?
I'm calling from about 1,000 feet from the ocean in Southern California.
Southern California, very close to us. Thank you for your question.
Thank you very much. Thank you for the tour.
Of course. So if anybody else wants to ask a question, you can also just, if you're shy and you don't want to enable your camera, you can also just enable your microphone. Maybe if that gives an incentive to join for a question. And if not, Andreas, I think that was a very comprehensive tour of the facility.
Yes, if there are no more questions, so we have done a good job, I think.
I think so. And of course, there's so much more that is to be seen in this factory. We had a real tough time to edit it down. just 30 minutes. The original was like an hour and 20 minutes. But I hope we can soon release a more complete version of the video for everybody to access.
That would be nice, yes.
Yeah, and of course we have this session recorded, so this will be available to you over the next by the end of the event. That's for sure. And yeah, I'll let you close it, Andreas, as you wish. I extended the session until 4, so if you want to all have a beer together, we can still do that here as well. But
okay,
off to you.
So Benjamin, thank you very much for the chance to do this tour with all of you. And yeah, thank you very much for participating in this virtual fab tour. We hope that it was interesting for you and that you could gain new insights. And if you have any questions in the following time, so please feel free to contact us via the addresses on our website, for example. Just drop an email. We are willing to answer all of your questions. And if you come along in Germany, so you are invited to visit the plant personally, of course. So thank you, thanks a lot, and yeah, have a nice evening.